I'm going to go over a real-world example of phylogeny and how you can have paraphyletic and polyphyletic groups. So hopefully if I put it, the idea is that if I put it in terms of species that you're familiar with in a context that you already know, that it will make more sense than species A, B, C, D, E, whatever. So I'm going to give the example of reptiles, birds, amphibians, mammals, how they're all related to each other. And some of you may know this. It may have been covered in some of the classes, some of you may not. But it's pretty interesting when you start looking at the relationship between all of these different groups. So let's start out and think about birds and dinosaurs first. So are you all familiar with the idea that birds and dinosaurs are really closely related? Yeah. When I was a kid, that wasn't what we were taught exactly. So it's been within my lifetime that paradigm has shifted. So if you look at the relationship between birds and different dinosaurs, let's start out over here. And we'll put birds. Let's turn out the light. Okay, birds. And the closest relative to birds are meat-eating dinosaurs like T-Rex, velociraptors, those types of things. So I'm just going to put T-Rex here to represent all of these carnivorous meat-eating dinosaurs that you're familiar with. So if we go back in time a little bit to this next node, and you draw a relationship, then you have the sauropods. So that's Littlefoot. Is Land Before Time a little bit too old? Okay, good. Land Before Time, Littlefoot, long necks. Those are the sauropods. Littlefoot. So the first thing to notice that's kind of interesting is that modern-day birds and the Tyrannosaurus rex are more closely related to each other than a T-Rex is to a sauropod. Okay, if we draw the next one, so let's go back out here. And these guys over here are what are called bird hip dinosaurs. So an example or representative of this would be the Triceratops. Okay. Ooh. I think I spelled that correctly.
Sorry, how do you spell that?
Triceratops. All right, so now we're getting into extant territory again. So the crocodiles, or the crocodilians group. The crocs, so alligators, those types of organisms. Bring it out a little bit further. And here we have our lizards and our snakes. Lizards and snakes. Just a couple more groups here. So these are the cute ones, these are the mammals. And then this might be surprising to some of you. We have amphibians out here, so frogs, salamanders, those types of things. Amphibians. Okay, so this is our tree. And I'm going to give an example of different ways that people have grouped organisms, and then we'll take a look at them and see if that constitutes paraphyletic or polyphyletic groups. So first, let's categorize the animals that are defined as reptiles. Okay, so reptiles would be the crocodiles, lizards, snakes. I think, yeah, those would be our traditional reptiles. Now, would that be, what type of group would that be? Monophyletic, poly, or para? Let's draw this, so if we were to draw that, they all share a last common ancestor right here, but it excludes these organisms right here, the dinosaurs and the birds. So that would be a paraphyletic group. It's one group that we're talking about, but while it encompasses the last common ancestor, it excludes descendants. Does that make sense? Okay. So now let's talk or give an example of the groups of organisms that are traditionally studied in herpetology. And I will not choose green because that would just be mean to anyone who's colorblind. So let's see. We've got blue on there already. Get a nice purple in there. Okay. So, herpetology. So, if any of you have ever taken classes or know who Bobby Espinoza or Jeannie Robertson are over in ecology, they would be herpetologists. And they traditionally study amphibians, and then lizards, snakes, crocs. So lizards and reptiles. Or I'm sorry, amphibians and reptiles. So if we were to draw a circle around that, we would have the same group that the reptiles are in, and then you'd have this additional one. So would that be poly, para, or mono?
Para.
Para? Not quite. It's poly.
Why? Because it gets...
Yeah, because it doesn't, it excludes not only these groups right here, but this group. So you can't encompass the last common ancestor right here because of the mammals. So we've got two separate groups that you're drawing. And so that's poly. And, poly anything, polyamorous. You've got multiples rather than one group. So that's one of the key differences between poly and para. If you can remember that, that'll help you a lot when you're thinking about trees. Questions on that? Yes?
Can you find out poly?
Poly and para?
Yeah.
Yeah, okay. So that's a good question. I'm going to pause this. So in a paraphyletic group, so like the reptiles, you have a group of extant species or terminal branches that when you circle them or when you group them, they all include the last common ancestor. So everything, or all of the taxa in here are covered by the last common ancestor, okay? And these groups are excluded. Okay, so you have a last common ancestor, and all of the groups that are not downstream. This paraphyletic group right here, if you circle them, everything within this is not included in part of the last common ancestor. So here you've got the mammals, and you can't circle this group entirely because the mammals are there. So you have to draw two separate groupings to explain the relationship between those species. So you have to draw two separate circles around them, essentially. Because otherwise, if you drew a circle around everything, that wouldn't represent a group because you'd have something in there that was not a part of the group. So that's the difference. Does that make a little more sense? Okay. Any other questions on that? Okay. So today we're going to do a little bit more tree stuff, go over some of the basics. And then what we're going to do is jump into an exercise where you will be building your own trees. And what I've done, I did this year, or I did it last year for the first time, and I'm going to do it this year, is instead of having you listen to me during class explain how to do it and then go home and do it, what I'm going to do is, well, I already have actually, is post a link to a YouTube video that's a tutorial on how to do it. And then on class time on Wednesday, you guys are going to come in and work on it. So you'll work on it independently, but when you run into issues, then you can ask people around you, and you can ask me for help. And that seems to be a little bit more effective way of solving this kind of problem that is what I call tree thinking problem as you get into it. So for the rest of the lecture, we'll do some more basics, and then I'll give you a few things that you need to know before the tutorial, before you jump in and listen to this tutorial. So this is where we left off last time, and we had this tree where at one point along the way, there was some type of change or mutation, that the character trait was still present, but the state was different. And now we're going to talk about how we define the different states that we see. And the first that we're going to talk about is what's called an ancestral state. So an ancestral state is the character state that was present in the last common ancestor. So in this particular case, if we're just looking at the extant taxa, so the organisms that we're studying, and we look at the purple or the blue state and the pink state, the blue state is the ancestral. And we can say that because this was the trait that was present in the most recent common ancestor. So the ancestors of all of the taxa that we're looking at had the blue smiley face. So now let's think about the state, the orange frowny face state. So these guys, and this is considered the derived state. So this occurred sometime after this mutation occurred sometime after these two groups split. So after the split from the most recent common ancestor. So this frowny face state was not present in the most recent common ancestor, and therefore it's called the derived state. Make sense? Derived versus ancestral. And an example of that would be the last common ancestor between humans and chimps. So the ancestral state is a lot of body hair. So our last common ancestor before we split likely had a whole lot of body hair like current chimps do. But along the way there were some mutations and we lost most of our body hair. So that would be considered the derived state. So now we're going to define a term that you'll see a lot when people are talking about phylogenetic trees. And the term sounds more complicated than it is, and it's called the synapomorphy. And to help you remember this or think about it, its derivation is from the Greek, and syn, so that's shared. You've heard of syntrophic or syn this, syn that. So syn, synapomorphy, is shared. Apo means away from, so derived. And then morphe is a shape or character. So you put those three things together and you get the definition. Let's just take a look at an example. So here's our usual tree, and it's been divided into two groups. And in these two groups, mutations have occurred along the different branches. So in this particular branch, you have mutations occurring here, here, and here. So the question is, which one of the, or how many of these species would have mutation 1? Would all of them? Would some of them? All of them. Yeah, all of them would have mutations 1, 2, and 3 because they occurred before the last common ancestor. Likewise, over here, you have a couple of mutations. And so all of these would have 4 and 5. So 1, 2, and 3 would be what's called a shared derived trait. So over here, 1, all of these have mutation number 1, and they share it, and it's also derived versus ancestral. So the last common ancestor to these guys didn't have it, and so it would be derived, shared derived trait, as opposed to a trait that is shared and ancestral. That wouldn't, ancestral shared trait wouldn't be a synapomorphy. That make sense? Okay. So likewise, within this group, mutation 2 would be a shared derived trait, and among this group, mutation 3 would be a shared derived trait. Same thing for the other side. Among all of these organisms, 5 would be a shared derived trait, or a synapomorphy, as would 4. So does that make sense? Questions on that?
So
Yeah.
to be clear, for species D through F, they also have the ancestral 1, 2, 3.
Yes, that's correct. So D through F would have the ancestral trait for 1, 2, 3 because no changes have occurred along that lineage. Yeah.
So would be that, or because I guess when you put 1, 2, 3 on like this,
Uh-huh.
on like right after the NCA, it kind of makes it like that. I guess it's exclusive.
Yeah, oh, okay, so I think I get what you're saying, like it's exclusive, but it's not an appearance of something new, it's a change. So that's a good point. So if we put that into perspective, let's say that we have, a DNA sequence with 5 different nucleotides. So we'll just call it A, T, T, C, G. And let's say that our ancestral organism had that particular sequence. So along this lineage, the first thing that happened is nucleotide 3 changed. It mutated. So let's say that nucleotide 3 changed from a T to a G. So all of our species down here at position 3 would have a T, or would have a G instead of a T. Draw an arrow. And this particular group would still have a T. So it's not that 1, 2, 3 indicates an absence or a presence, it's that it's just a difference. So let's go through the whole thing to make sure that that makes sense. Let's say that position 3 changed from a T to a G. Let's say position 2 changed from a T to an A. And let's say position 1 turned from an A to a C. So what you would end up with, let's see, position 1 turned from A to a C. So that would be C, because we're changing from A to C at position 1. Position 2 would be A. Oops. Because at position 2 we changed from a T to an A. And position 3 would be G, because we changed from our T to a G. And then the last two would remain the same, C, G. Okay? Now on the other lineage, we had position 5, and that may have changed, let's see, it starts out as a C. Let's say position 5 changed to a T. And position 4, oops, position 5 is a G, sorry. Position 4, let's say that changed from a C to an A. So if we're writing the sequence for the last group of organisms, 1, 2, and 3 is going to be the same. Positions 1, 2, 3 are going to be the same as ancestral. There were no changes there. So it's going to be A, T, T. But then position 4 changed from a C to an A. And position 5 changed from a G to a T. So, in both cases, it's not that you have something brand new arising, it's just that there's a change. Yes?
So the ancestral shared trait for the right side would be the ATT?
Yeah, so the okay, for the right side,
Yeah.
this side,
Yeah.
the shared derived trait, or the synapomorphy, would be positions 4 and 5, an AT at 4 and 5. That would be the synapomorphy, shared derived trait. Yeah. Oh, yeah, this sequence is what the most recent common ancestor had. Yeah, so this is the sequence of the most recent common ancestor. Yeah?
I think for the question, I think she was explaining, how you do the shared derived trait, and then you for the 4 and the 5 on the right side, you change that to the A to the T. The shared ancestral trait would be the ATT still, right?
Oh, yeah, the ancestral would be, the shared ancestral would be the ATT. Yeah, but we don't really have a name for that, like synapomorphy. We'll just call it the shared ancestral, or the ancestral trait. Other questions? Okay. All right. Now we're going to jump into a few more descriptions and definitions of trees. And we're going to talk about something called convergent evolution. Now, just to get a handle again so I know where you're coming from, how many of you have a pretty decent feeling that you know, or a pretty decent idea of what convergent evolution is?
It's analogous.
Yeah, it's analogous, but just by a show of hands, like, pretty good? Okay, a few, I see kind of half, so. All right. For your studying convenience, these are the definitions. I'm not going to read them to you because they won't make sense, but when you go back and study, those are the formal definitions. Instead, I'm going to show you what I mean by convergent evolution and evolutionary reversal. Let's see. Again, this will be nice for when you're studying, but if I read it aloud, it's not going to make much sense. Let's get to the pictures. Convergent evolution. Oops. All right. So here we have our favorite tree that you might be starting to love or hate. I won't make you tell me which one. And our most recent common ancestor has a head but no face. And again, we're going into this model where there was the most recent common ancestor that split into two different branches, and each inherited the head with no face. One of the lineages, right here, evolves, there's some type of mutation, and the mutation was favorable, so it went through the population. Anyway, this one lineage evolves a face with a frown. And the time continues to go forward. There's continuing evolution, and over here, the descendants maintained the no face, and over here, the descendants maintained the frowny face. And it continues, and it continues. But let's say that one of our lineages over here also evolved a frowny face. But we're going to color that red because the mutation that occurred is completely independent of the mutation that occurred over here. Even though the mutation gave rise to similar states, they're completely separate. And so if we draw the locations where that happened, this happened up here early in the evolutionary history of this group of organisms. And this happened down here later. Now, some examples of convergent evolution that you may be familiar with. This is the body hair example. So humans and elephants generally lack body hair. And that didn't occur once in evolution. That occurred in our lineage in the past 5 million years. We lost our body hair. And then elephant lineages all on their own lost their body hair. And it was probably for very similar reasons. The conditions on the savanna, being able to sweat, getting cool, those types of things probably led both of us, or both of our species, to lose body hair, but it happened independently. You have the example of a sugar glider and a flying squirrel. Both are mammals that have evolved this membrane connecting their legs and arms so that when they jump out of trees, they can glide. And this didn't happen, this happened separately on different lineages, and you can imagine the selective pressures that would drive that. Here's one cool example, is that the human eye is a pretty neat, complicated feature, but it turns out that the octopus eye is really similar, and those eye structures evolved independently. And here you have in Patagonia and in Australia, two different mammals that have developed very similar body types, similar strategies. So these are examples of convergent evolution. So when we're talking about convergent evolution, it becomes a challenge to figure out, if you've got two organisms that have similar character states, it's difficult to figure out whether that occurred twice or whether that occurred once. So what I mean by that is, let's say you have, what example can we give? Let's just do the human and elephant example. So you have humans and you have elephants. And if we, draw a tree here, at some point humans and elephants are related. And the question is, does the most recent common ancestor have body hair?
Yes.
Or are they, well, we'll just call it bald for convenience sake. Or are they bald? And if we're just looking at humans and elephants, like if we're not taking any other species into consideration, it would be really hard to know. But if we consider, here we have all of these other mammalian species, so other mammals. And of course here you're going to have other mammals. It makes much more sense for the most recent common ancestor to have body hair. Because for that to occur, you would need to have a change on our lineage and a change on the elephant lineage. However, if, we'll do in red, if bald is the ancestral state, if bald is ancestral, what would have to happen is that body hair would have to arise here, maybe in here, and then you'd have to have a change back over here and over here to bald, or some other pattern of unlikely events. So it just makes a lot more sense if body hair was the ancestral state. So that's one way you can distinguish between convergent evolution and, and identity by common descent is how likely those scenarios are. Yeah?
Why would it have to arise twice on each of the lines?
Okay, so let's say that balding is the ancestral state. So all of these mammals over here have to have body hair. So there would need to be a change here from bald to body hair, so that all of these guys could have body hair. And then here, in order for us to be bald, it would have to change back from body hair to bald. And the same over here. All of these other mammals have body hair, so there'd have to be a change from bald to body hair, and then another change from body hair back to bald over here. So you have to have a really contrived explanation about evolution if bald was the ancestral state. It's just so much more simple and likely that body hair is the ancestral state and that you just had two changes along the tips of the lineages. Yeah?
So what you're talking about is the evolutionary reversal? So
No. This isn't reversal because we're not reverse. Oh, yeah. So, okay. So the example where body hair is ancestral, that's convergent evolution. But in our example where bald is ancestral, that is reversal. Okay, and we haven't gotten into that, but yeah, very good point. If we look up here, and actually go into the point that you just brought up, leading us into the next part, we have our observation that two organisms have similar character states. So again, humans and elephants. Possible explanations include convergence. So that's what we talked about, the convergent evolution, where you have a mutation along elephant lineage and a mutation along human lineage. That's convergent. Another explanation would be evolutionary reversal, which is what I was talking about here. So you have bald that goes to body hair that goes back to bald. So that's what's called a reversal, is when you have a change back to the ancestral state. So you're essentially reversing what happened on the evolutionary lineage. We'll go through another example of this. And I just answered the question actually in words, but this is for your studying pleasure, an answer written down in text. And we'll do the bird and bat flight as an additional example of that. All right. So in this particular example, we're going to have two models or two hypotheses when we compare bats and we compare birds. So both of these bats and birds have flight. And so we want to know, are wings ancestral? Or so did the last common ancestor of birds and bat have wings? Or are they derived? Did the bird lineage evolve wings on its own and the bat lineage evolve wings on its own? So these are our models. Wings are ancestral or wings are derived. Now if we draw in the tree right here, so we have mammals and we have bats here. And here's our reptile group that we talked about, even though birds aren't really reptiles. And you have birds right here. Okay? So if wings are ancestral, so here we have defined our model that wings are ancestral. If wings are ancestral, the most recent common ancestor to everything would have had wings. And what would have had to have happened is if this is ancestral, all of these lineages here, all of these common ancestors would have had to have wings because these birds and these bats ended up having wings. And what would have had to have happened is that a bunch of groups would have had to have lost wings. Group A, C, D, E, G, F. And how likely do you think it is? Very unlikely for a flight to have been lost a bunch of times. Now let's say that no wings are ancestral. The last common ancestor to mammals and reptiles did not have wings, as indicated right here. And if you reconstruct the history for all of the nodes, all of the nodes in the tree, you find that in this particular case, you only have to have these two events to occur. You have to have wings evolve in the bird lineage and wings evolved in the bat lineage. So in this particular example, convergence rather than reversal or not reversal, but rather than homology due to common descent, the convergence would be the more likely answer. Okay. Questions on that? This is one of the nice things in biology, actually, is that, instead of making inferences about convergent evolution can be a little bit more straightforward if you already have the tree, because you choose the most likely route. And it's a pretty nice, straightforward thing to do rather than build all sorts of mathematical models to build the tree in the first place. That's the harder part. Okay. So that is all of the lecture material with the slides I have today. So in the last 10 or so minutes of class, I'm going to go over some background that you need to be able to go through the tutorial tonight or before class on Wednesday. So we've talked a little bit about how we build phylogenetic trees, and we just have brushed on it momentarily. And one of the ways, and in fact, the primary way that phylogenetic trees are built nowadays is through using DNA sequence. So we compare the DNA sequences of extant organisms, and we can use those use those DNA sequences to infer the trees. So let's take an example, and we have species, let's call it D, E, and F. So species D, species E, and species F. And they all have a particular DNA sequence, and we're going to make it, we're going to start out the example with a pretty basic example. For the DNA sequence, D is going to have an A, T. See that? Yeah. Species E is going to have an A, C, T. And species F is going to have A, G, A. Okay, so those are the sequences. And the way that those came about, if you build a tree based on those sequences, would be something like this. So here you have our last common ancestor. And the last common ancestor in this case had 3 A's. In the last common ancestor, there was a divergence, so it split. And somewhere along the line, the last A in this sequence, so it started with A, it changed to a T, A, T. So, and then at some point, there was another divergence. And along this lineage, there was a split or a mutation, and it went from AAT, because this had to have AAT, right? You understand why this has AAT and not AAA? Yeah? Okay. So let's say there was a change to ACT. So the middle nucleotide changed. Now, over here, let's say there wasn't any type of divergence, no speciation event occurring, but somewhere along the lineage, there was a mutation. So AAA went to GAA. So at the end, if we're looking at what's there, here's species F with the GAA, so that's F. Species E has an ACT, and species D has an AAT. Okay? On board? Questions? Good? So the first step then in building a tree is to count how many differences there are between the different species, and that provides the base information for building your tree. So let's take species D and E. So we're comparing species D and we're comparing species E, and let's just count the number of differences between D and E. So there's one difference between D and E. Now, if we count the differences between D and F, so here's one difference, 2 differences, and 3 differences. Oops. Oh, yeah, I'm sorry. Yes, yeah, so D, the first one is different, the middle one's the same, and the third one's different. Yeah, sorry, 2. And then E and F, this is where we have 3 differences. So the first one's different, the second one different, and the third one is different. So by counting those differences, now we can start to quantify how different those different species are. In this particular case, you can see that 1 and 2 are similar to each other, and that E and F is different, somehow an outlier. So what the tutorial is going to teach you that you're going to look at is how to take that count information and to make a tree from it. So a couple of notes about that. Watching the tutorial is mandatory. I suggest that you watch really well and take notes just like you would in class instead of just kind of turning it on and having it in the background. You know, pause it, make sure exact what you know, what steps I'm doing, that you know why I'm doing it. So that way when you come to class, you'll be prepared to do your assignment, because you're going to be way behind if you have to start out in class off to the side watching it. You're not going to get any of the benefits of solving the problems with the help of colleagues and friends. So watching is mandatory. And the link is already up on Moodle, as is a set of notes that I put together for you to have as a reference. Any questions on that? Nope? Okay. So that's what I have for lecture today. Let's meet back here at 2 o'clock for the start of lab.